Stand beneath the enormous glass roof of a major Dubai shopping mall at exactly noon, and you will notice something missing. The Arabian sun is pouring through thousands of square feet of transparent skylights, illuminating polished stone floors and thousands of wandering tourists. Yet the air around you feels perfectly chilled. It is an engineered illusion that completely hides a brutal physical reality. The exact same sunlight that makes these interior spaces feel so spectacularly open is continuously pumping massive amounts of solar radiation directly into the building envelope. Every photon carrying heat into that space represents energy that a hidden mechanical system must violently force back out. So how does a gigantic sunlit atrium in the middle of a desert not immediately overheat? Dubai has spent the last 2 decades constructing some of the most impressive interior environments on Earth. These towering atriums are not just architectural showpieces. They serve highly specific commercial functions. A massive skylight provides natural daylight that reduces the psychological feeling of being trapped inside a giant box. It creates visual scale, makes navigation intuitive, and transforms a simple retail corridor into a luxury destination. But in a climate where summer temperatures regularly approach 50 degrees Celsius, glass creates a fundamental contradiction. In most hot environments, traditional architecture naturally evolved to feature thick walls and small windows to keep the hostile climate out. Modern Dubai has essentially inverted that logic. It builds colossal transparent envelopes that invite the desert sun directly into the core of its structures. Admitting that much sunlight can never be treated as a purely aesthetic decision. It is a deliberate choice to invite extreme solar heat gain into a structure that desperately needs to remain cool. If the primary engineering goal is to maintain a comfortable temperature inside a giant building, why deliberately create a massive transparent opening pointed directly at the sun? To understand the scale of that problem, you have to look at what physically happens once solar radiation crosses the glass. Think of a glass atrium as a gigantic transparent container. As solar radiation passes through the overhead glazing, it does not immediately heat the air. Instead, the sunlight travels downward until it strikes the solid interior surfaces. It hits the marble floors, the structural steel columns, the retail storefronts, and the furniture. Those solid materials absorb the incoming solar radiation. The energy excites the physical molecules within the stone and steel, causing the surfaces themselves to grow significantly warmer. Once those vast surfaces heat up, they begin transferring that thermal energy into the surrounding indoor air through convection. As the adjacent air absorbs the heat, it becomes less dense and more buoyant. That freshly warmed air then begins to steadily rise toward the ceiling. Because the sun never stops shining during the day, this process is continuous. Energy is perpetually entering the transparent container and converting into trapped heat. Thermal comfort only exists inside that massive space because heavy cooling equipment is simultaneously running to pull that exact same amount of heat out. It is a relentless mechanical tug-of-war between the sun and the air conditioning. But this is not just theoretical physics. Designers in Dubai actually have to confront the reality that they are sometimes letting too much of the sun inside. This thermal battle is a heavily documented phenomenon within the city's own commercial infrastructure. Researchers studying natural lighting and energy efficiency have closely examined the vast skylight systems in major retail centers like Mercado Mall, Mall of the Emirates, and Dubai Hills Mall. These specific public spaces are highly dependent on expansive overhead daylighting. When engineers ran thermal and lighting simulations on the Dubai Hills atrium configuration, they uncovered a revealing baseline metric. Before applying advanced architectural optimization strategies, the modeled average illuminance under the skylight hit approximately 11,938 lux. That is an overwhelming flood of raw solar energy. Through careful architectural optimization, researchers demonstrated that this intense exposure could be successfully reduced to roughly 3,157 lux. That specific drop in numbers illustrates a crucial reality about Dubai's architecture. The fundamental challenge in this city is almost never about figuring out how to get enough natural light into a building. The engineering challenge is aggressively controlling how much of that intense light is allowed to enter, and precisely where it is permitted to go once inside. Field observations of these giant interior spaces frequently reveal secondary shading measures deployed around upper retail levels just to manage the intense direct exposure. Light is only the visible half of this architectural equation. The other half is the invisible operational toll this solar load takes on the machinery keeping the building alive. When you scale this localized problem up from a single shopping mall to the entire urban grid, the stakes become staggering. According to the Regulatory and Supervisory Bureau of Dubai, in its 2024 annual report, the estimated electricity demand for urban cooling across the city was 26,338 gigawatt-hours. To put that immense figure into perspective, cooling alone represented approximately 49% of the total electricity demand on the entire grid that year. To be absolutely clear, giant glass atriums do not consume half of the city's power by themselves. But they are one of the most extreme physical examples of why solar heat gain matters so much in this specific climate. Every single watt of solar energy that a commercial building envelope fails to block is a watt that the mechanical cooling system must eventually pay to remove. So an obvious question arises. If cooling is already one of the heaviest burdens on the electrical grid, why not simply use heavily tinted, nearly opaque glass to block out almost all the incoming heat? The answer is that doing so would completely destroy the commercial and psychological purpose of building the giant atrium in the first place. This converts the situation from a simple case of bad design into a deeply complex optimization problem. And one of the most famous landmarks in the city reveals exactly how far Dubai engineers will go to solve it. The iconic Burj Al Arab features a triangular atrium that rises approximately 182 meters into the blazing sky. Given its massive scale and prominent coastal location, you might expect the southern face of this colossal void to be sealed behind one gigantic conventional glass wall. But the structural designers deeply understood the physics of the Arabian climate long before the first piece of steel was placed. Instead of trying to solve the problem of giant glass by simply engineering even more advanced glass, they successfully changed the envelope strategy entirely. The massive southern expanse of the towering atrium uses a specialized glass fiber fabric screen attached securely through a complex structural cable system. This brilliant architectural cheat code allows beautifully diffused natural daylight to flood deep into the interior volume. Simultaneously, it drastically reduces the overall solar heat gain by permanently eliminating the need for standard transparent windows across that entire sun-facing exposure. The Burj Al Arab is not suffering from a thermal crisis or struggling to maintain its internal temperature. Instead, it serves as towering physical proof of how seriously solar gain had to be treated right from the conceptual design stage. It proves that you cannot just build a massive transparent box in this brutal environment and expect the air conditioning to magically fix it. But what about the massive commercial atriums that really do rely on enormous glazed skylights? They survive through a heavily layered, almost entirely invisible mechanical defense system. The battle to keep a giant glass atrium cool is fiercely fought in multiple distinct layers. The first vital line of defense is stopping the solar radiation before it ever becomes an indoor load. If you look closely at the expansive skylights in the Dubai Mall, you will clearly see strategic shading systems integrated directly into the surrounding architecture to physically block the most intense direct glare and excessive heat gain. The second defensive layer relies on the chemical composition of the glass itself. These modern structures utilize high-performance double glazing alongside specialized low-emissivity coatings. These microscopic layers emit a large portion of the useful visible light while bouncing a significant amount of the unwanted infrared heat energy directly back outside. But even the most advanced architectural glass is held together by metal frames, and metal is an excellent conductor of environmental heat. To actively counter this thermal bridge, prominent locations like the Dubai Marina Mall utilize what are known as thermally broken frames. These specialized window frames contain rigid insulating materials placed right in the middle of the aluminum extrusions to snap the chain of heat conduction from the scorching exterior to the deeply cooled interior. The fourth layer of thermal defense moves beyond the skylight entirely and into the solid surrounding envelope. In the existing Dubai shopping mall atrium energy study, researchers definitively found that simply improving the roof thermal insulation produced an approximately 7.5% reduction in modeled atrium energy consumption. The fifth layer directly connects the movement of the sun to the electrical demands of the power grid through automated lighting controls. Admitting natural daylight becomes entirely wasteful if thousands of artificial indoor lights remain fully active while the sun is intensely shining. In that exact same energy study, integrating automated indoor light sensors produced an additional 8.5% energy reduction. The financial logic here is vivid and constantly compounding. Artificial lighting draws electricity from the grid, but it also produces its own localized waste heat. If the heavy lights stay on, the commercial cooling system has to burn even more power just to actively remove the heat generated by those redundant bulbs. When all of these localized improvements were modeled together by the engineering team, the combined optimization produced an impressive approximately 20% reduction in total atrium energy use. But even a highly optimized thermal envelope cannot magically stop every single watt of thermal energy from crossing the barrier. And once that lingering heat finally makes it inside a massive interior volume, gravity fundamentally changes the nature of the engineering problem. When thermal energy finally penetrates the envelope and significantly warms the interior surfaces, the resulting warm air immediately becomes buoyant. It rapidly rises. In a standard residential room, this is easily managed, but inside a towering commercial atrium, this physical reality creates a complex phenomenon known as vertical thermal stratification. The enormous uninterrupted height of the space allows the indoor air to naturally separate into highly distinct temperature layers. Specific academic research into glass ceiling atriums has clearly found that solar radiation and heat transfer through the roof can significantly intensify this vertical thermal stratification. This scientific reality means that a wealthy shopper standing on the polished ground floor may feel a perfectly chilled, heavily conditioned breeze. But tens of meters directly above that person, the invisible thermal environment is behaving completely differently. A massive pool of significantly hotter air continuously accumulates near the expansive ceiling, constantly pressing against the upper structural elements. This creates a brilliant and highly effective narrative reversal for the building itself. The massive vertical volume actually helps the overarching architecture effectively hide the thermal struggle from the thousands of people standing at the bottom. The heavy machinery works aggressively to keep only the lower occupied zones comfortable, allowing the waste heat to escape upward where no one can actually feel it. The building is not failing, and the massive glass ceiling is certainly not cooking the occupants below. The entire cavernous space is carefully and continuously managing a highly invisible thermal boundary. Just when it seems that rising sensible heat is the final enemy the engineers have to fight, the regional climate delivers an entirely different kind of ambush. Heat is far from the only burden placed on the massive cooling infrastructure. Many international visitors mentally classify Dubai as a completely dry, relentlessly arid desert. But the towering city sits directly on the shimmering coast of the warm Arabian Gulf. During the grueling summer months, extreme daytime heat can routinely coincide with absolutely suffocating levels of coastal humidity. This geographical reality fundamentally changes the immense physical burden placed on the commercial buildings. The massive air conditioning networks are no longer just tasked with lowering the air temperature, which mechanical engineers refer to as sensible heat. They must simultaneously rip thousands of gallons of suspended moisture completely out of the air, dealing with what is known as latent heat. A 2026 academic study published in Nature Cities specifically used Dubai as one of its primary urban examples to measure this exact invisible burden. The researchers clearly found that air conditioning energy temperature sensitivity increases sharply as relative ambient humidity climbs. Under highly similar temperature profiles, days experiencing between 80 and 90% relative humidity could show an air conditioning demand that was 2 to 7 times more sensitive to temperature than days where humidity stayed below roughly 60%. To be extremely clear, this specific statistical finding does not mean the entire city suddenly uses 7 times more total electricity. It means the mechanical cooling infrastructure becomes hypersensitive to every single rising degree of heat when the surrounding air is completely saturated with water. Across the broadly affected conditions measured in the study, the actual air conditioning energy demand on highly humid days could be roughly 2 to 3 times higher than on comparable non-humid days. Suddenly, the central concept of the solar furnace expands drastically. The atrium is no longer just fighting a straightforward war against the blazing sun. It is simultaneously battling solar heat, ambient outdoor heat, the heavy moisture carried by the coastal wind, the heat generated by thousands of human bodies, and the thermal load of its own artificial lighting. Every giant transparent space in the city is a fortified mechanical fortress constantly fighting a highly complex multi-front war. If these massive transparent spaces require so much mechanical effort, why does Dubai keep relentlessly building them? Because a giant atrium is not just a thermal liability. It provides immense commercial and psychological value that simply cannot be replicated by solid concrete walls. Skylights create visual scale, make massive retail complexes intuitively easy to navigate, and offer a vital psychological connection to the outdoors without exposing people to the hostile temperatures. When properly controlled, they also significantly lower the building's daily reliance on expensive artificial lighting. This is why major daylighting studies on Dubai malls never conclude that skylights should be permanently eliminated. Instead, engineers rigorously test architectural variables like the skylight-to-floor ratio, visible light transmission, glass orientation, and the geometric dimensions of the atrium itself. The real engineering challenge in this extreme environment is almost never a simple choice between building with glass or building without it. The actual question is exactly how much sunlight a building can financially benefit from before that exact same sunlight becomes an unstoppable mechanical liability. And in Dubai, answering that fundamental question is not left entirely to the discretion of individual architects. If you look closely at the historical framework of the city's mandatory building regulations, you can clearly see exactly how seriously the local government treats the unforgiving physics of solar radiation. Dubai regulators did not simply discover the complex problem of solar heat gain in recent years. Long before the current era of hyper-modern sustainability frameworks, local technical guidelines consistently contained highly specific requirements dealing directly with the entire building envelope. Structural engineers have historically had to carefully meet strict criteria for standard glazing, overall heat transmission, specialized shading coefficients, and deep thermal insulation. By the 2010s, comprehensive green building requirements became entirely mandatory for new commercial construction across the rapidly growing city. These crucial environmental standards were eventually refined and deeply integrated into overarching frameworks like the Dubai Building Code. This detailed regulatory history is not evidence of a sudden municipal crisis, but rather clear evidence of a highly controlled environmental baseline. Dubai's perpetual war against solar gain is not just fought quietly in hidden mechanical rooms or concealed behind advanced glass coatings. The complex defense system is quite literally written into the strict legal regulations that fiercely govern exactly how the city is fundamentally allowed to be built. Return mentally to that spectacular opening image of a casual visitor standing directly beneath an enormous desert skylight. The intense sun pours completely unhindered into the sprawling retail space, yet the expansive room mysteriously feels perfectly cool and entirely safe. That apparent normality is actually the final engineered result of a massive, heavily regulated thermal war. Hidden directly behind that flawless human experience is a staggering array of tightly controlled glazing, strategic shading, deep insulation, automated controls, and rigorous building regulation. The ultimate goal of all this invisible machinery is to make the human occupant entirely unaware of the violent climate battle happening mere inches above their head. The sprawling atrium is truly impressive because it successfully creates the vivid sensation of standing almost outdoors, while methodically engineering away all the brutal thermal consequences of actually being outdoors in Dubai. A much subtler and infinitely more expensive form of true luxury is the quiet ability to stand completely exposed beneath the Arabian sun without ever having to feel it. As Dubai continues relentlessly pursuing interior spaces that are somehow larger, exponentially brighter, and far more open, a lingering structural question naturally remains. At what exact point does the massive hidden engineering required to systematically defeat the desert climate become exponentially more extraordinary than the visible architecture itself? The phrase solar furnace is used throughout this documentary exclusively as a narrative metaphor to accurately describe the severe solar heat gain challenge created by large glazed spaces in hot climates. It is not a literal claim that the specific Dubai buildings discussed today are fundamentally unsafe, structurally uncontrolled, or actively operating as dangerous literal furnaces. Many of the architectural examples highlighted in this story actively demonstrate the exact opposite reality. The complex engineering is specifically designed to prevent indoor overheating and limit excessive energy use. Dubai's most fascinating structural engineering often exists entirely hidden within the complex mechanical systems that wandering tourists never get to see. If you want to truly understand the invisible infrastructure that continually keeps this extreme city running safely, subscribe to the channel and join us for the next technical investigation.